In this video, I want to give you an overview of circuit analysis. So, if you remember from before, I said that there are 5 major branches of electrical engineering. So what is common in all of the previously mentioned branches? So definitely electrical circuits. So an electric circuit, generally speaking, is a mathematical model that approximates the behavior of an actual electrical system. So circuit theory is a special case of electromagnetic field theory, which studies the static and moving electric charges, right? So as you see, circuit theory is a special case of the field theory. So you might ask, why don't we use the generalized field theory to describe and solve electric circuits? The answer to that is it is very difficult and cumbersome, and it usually requires advanced mathematics, right? So because of that, we will do the simplified version of the electromagnetic field theory, which is the circuit theory. If you are in the electrical engineering field, you will see more advanced models of electromagnetic field theory, especially in electromagnetic course. But for now, we use the circuit theory, and for all intentions and purposes, circuit theory is very capable in solving almost all the circuits that we will see. So there are some basic assumptions for circuit theory. So these assumptions are necessary for us to be able to simplify the generalized field theory. So the first important assumption is that electrical effects happen instantaneously throughout a system or a circuit. So what does it mean? So electric signals usually travel at or near the speed of light, right? So if the system is physically small, electric signals, you can say, move through it so quickly that we can consider the effect to be simultaneous at every point in the system. Because of that, we call such a system as a lumped parameter system. I will explain this a little bit more at the later slide. But you can see, because the speed of light is very high, and the circuit that we usually work with are very small, you can assume that the effect of any signal that we have that goes through the system is instantaneous at every point in the system. If it's not instantaneous, then we need to use more complicated equations to represent such a system. But for us, for now, we have this basic assumption. The second assumption says that the net charge on every component in this system is always zero. So what do I mean by the net charge? The meaning is that we don't have a component in our system that is positive, or we don't have a component in our system that is negative. So basically, no component can collect a net excess of charge. Although what we can have is that we can have both positive and negative charges in equal amount on a single component, right? So these are two different things. So for example, when you are working with capacitors, inside the capacitors, you have a part of the capacitor that collects the positive charge and a part of the capacitor that collects the negative charge, right? So if you look at the capacitor from outside, you should not see any net charge because the amount of the positive charge and amount of the negative charge are equal. And finally, for the third assumption, there is no magnetic coupling between the components in a system. So it means that we should not have any coupling between the components in a system. The magnetic component coupling can occur within a component itself, right? So when we talk about inductors later on, we see how we can have inductors that have several components that are magnetically coupled, right? So since this coupling happens inside the component itself, right, this assumption is satisfied. So how small a physical system needs to be considered a lump parameter system? So to answer this question, we need to know a little bit about the wave propagation phenomena. So if the wavelength of a signal is large, more specifically if we say if it at least 10 times compared to the physical dimensions of the system, we can safely consider that system to be a lumped parameter system. So now the question becomes, how can we measure the wavelength of a signal? So the wavelength, which is also shown with the symbol lambda of a signal, is the velocity of the propagation in that medium divided by the repetition rate. What is the repetition rate, or the frequency? Is the number of times that this wave oscillates in 1 second. And if you remember from previous video, frequency is measured in hertz. So let's just say we have a wave that is propagating in air. So if we have that, the speed of propagation is the speed of light. So 3 multiplied by 10 to the power 8 meters per second. So if we have this, and also we have the frequency of the wave as well, basically the number of periods of the signal in 1 second, dividing these two would give us the wavelength of the signal. So let's take a look at some examples. So in power systems, the operating frequency is 60 Hertz, or in some regions of the world, it's 50 Hertz, right? So if we assume the speed of light as the speed of the wave propagation, which is a safe assumption, the wavelength for this signal is going to be approximately 5 multiplied by 10 to the power of 6 meters, or 5 million meters. So because of that, if we have a system that is at least at most 10 times smaller than this, or it is the size is 500,000 meters, we can treat that system as a lumped parameter system. So as you can see, assuming that the speed of the wave propagation is fixed for all the electric signal that we are using here, it is inversely proportional to the frequency of the signal that we work with. So for the power system, the size of the system that can be considered as a lumped parameter system is very large. Why? Because the frequency that we work with is usually very small. But what about communication systems, which use radio signals that have frequencies in the order of megahertz or gigahertz, right? So let's just assume if we want to design a communication circuit that works with a signal in the order of 10 to the 9 hertz or 10 gigahertz. So for such a system, the wavelength will be 0.3 meter or 30 centimeters. So any system that is smaller than 3 centimeter can be considered a lump parameter system, right? So as you can see, as I said, because we are working at hugely different frequencies, the size of the system that can still be considered as a lumped parameter system is hugely different between the power systems and the communication circuits. So now that we saw this, let's just briefly go over the procedures that we follow for solving electric circuits. So the first step always is to identify what is given in the circuit. So whether it's the voltage at an element or the current through an element, right? Or if we have a voltage source or if we have a current source, right? So first we need to identify what is given in our circuit. And also we need to see what we are looking for, right? Because depending on what we are looking for, the solution that we have can be drastically different. After the first step, the next step would be to sketch a circuit diagram and some other visual models that can help us in solving the circuit. Step 3 is to think of several solutions for the system, and as we will move forward in the course, you will see how we can come up with several solutions for a single circuit. And based on those several solutions, or solution methods more specifically, we decide which one to choose between them. So you will see later on that we talk about node voltage method or mesh current method, right? Depending on the circuit, either of these can be simpler than the other one, even though both of them can be used to solve a circuit and both of them give exactly the same result, but one might be simpler than the other one, right? So you should have always these different methods in hand, and based on the conditions of your circuit, choose between the several methods to come up with the solution faster and more accurately. Based on this, and after we chose the method, we calculate the solution. So whether it's the current of an element or the voltage across a resistor, for example. In the process, it's always useful to use your creativity. What if there is a technique that you can use to simplify your circuit before even trying to solve it, right? So in that case, you should definitely use it, right? Because nothing is preventing you to use it. Because at the end, you are only looking for the requirements of the problem. The way you solve it, as long as the result is correct, does not matter. And finally, you should test your solution to see if it satisfies the conditions of your circuit. Because if it doesn't satisfy those conditions, that means that your solution is wrong. So we saw how we can solve a circuit. But what about if we want to design a circuit? So all designs begin with a need. So what do you need your circuit to be doing? So based on that, the answer to that question, is it possible to improve an existing design, or do you need to create something brand new? Because depending on your answer, you should take different routes. But generally speaking, there are some specifications for every design. The first specification is the concept, which can be either a sketch or a written description. Based on this concept, you create a circuit model that only consists of ideal circuit components. I will explain in more detail at a later video what do I mean by an ideal circuit component. After creating the circuit model, now is the time to do the circuit analysis and basically to predict the behavior of the circuit model and its ideal components. Depending on the result of the analysis, you may need to do some refinement so the output of the circuit model is closer to what you need. After these steps are done, then it's the time to build the physical prototype, in which you don't work with ideal components anymore. You work with actual electrical components. After you build the physical components, you do measurements and see if the results that you're looking for is being given by the physical prototype. If not, you may need to do additional refinements based on those measurements. In this video, we learned about the basic assumptions of circuit theory. I did a little bit more explanation on the lumped parameter systems and how we can see what is the appropriate size for our circuit to be still considered as a lumped parameter system, because if circuit is not a lumped parameter system, that means that the analysis is more cumbersome and it basically falls out of the scope of this course. And then finally, you saw what are the procedures in problem solving for electric circuits and what are the specifications that you need to satisfy if you want to design a new circuit.